This is the beginning of Chapter 7, Chemical Reactions and Quantities. Section 1 is Equations for Chemical Reactions. A chemical equation is used to represent a chemical reaction, which is what occurs when a substance undergoes a chemical change. Now, if you remember back to one of the first chapters, a chemical change is something that occurs when the underlying structure of a substance changes. So when a substance is converted into a new substance, one or more new substances that have different formulas and properties from the original substance, then we say it's undergone a chemical change. Now, we can't directly observe chemical change in most cases. We can't see the atomic or molecular structure of a substance. So the way that we infer a chemical change is often by observing physical changes. So we might observe the formation of bubbles, or a change in color, or the production of a solid, or heat being released or absorbed in a chemical reaction. Okay, so many of those themselves are physical changes, but they are physical changes that are accompanying a chemical change. Okay. In this example here, you have a picture of a silver fork which is tarnished into this dull black color. Okay. Now, a color itself is a physical property, but the changing of the silver color into the dull black color in this case is a physical change that has accompanied the chemical change where silver reacts with sulfur in the air to produce silver sulfide. Here we have some more examples of some types of evidence you might see for a chemical reaction occurring. And again, these are pieces of evidence. They're not necessarily conclusive. And on the other side, it's also true that you may have a chemical reaction occur where you don't see visible evidence for it. So you have to be very careful about how you characterize a chemical reaction. But in most chemical reactions, you'll see one of these types of physical changes. So you may have a change in color, like for instance in the tarnishing we discussed before, or in iron nails rusting into this dull reddish-brown rust color. You may see the formation of bubbles, like when you have calcium carbonate react with an acid, it forms CO2 bubbles. You may have the formation of a solid. In this case, you mix two clear liquids substances together, and they react with one another, and they form a new yellow solid, which forms this cloudiness that then settles to the bottom. This is a reaction called precipitation. Okay, this is an evidence of a chemical reaction. Or you may see heat or flame, right? The flame is heat and light energy being released from the reaction. So during combustion, this is often the case that you'll see these. A chemical equation fundamentally represents a transformation. It's a transformation of some substances into new substances. And so the transformation itself is represented by an arrow in the chemical equation, okay, which you can see here. This is basically the same thing as having an equal sign in a mathematical equation. But we use an arrow because we think about having some substances that you start with and then subsubstances that you end with. So it has sort of a direction from beginning to end. So on the left side of the arrow, you have the substances you start with that go into the reaction. These are called the reactants, the things that react. In this case, we have carbon and oxygen. Okay? On the right side of the arrow, you have the products, the things that come out of the reaction that you end up with. In this case, you have CO2, carbon dioxide. Okay? So you have reactants transforming into products. In real life, it looks like this. You have a piece of coal here, right? A big lump of coal, which is really just a collection of carbon atoms all stuck together in a certain arrangement. And then in the atmosphere surrounding the coal, you have all of these oxygen molecules. Now remember, oxygen is O2. It's a diatomic molecule. So each oxygen molecule is really two oxygen atoms stuck together, which you can see here. Okay? But when these oxygen atoms react with the coal, the carbon in the coal, under certain conditions, meaning usually with just a little bit of a spark or some sort of ignition, then they can react and form these new substances, this new substance, which are CO2 molecules, right? One carbon in the middle is this black sphere, and then each carbon is connected to two oxygen atoms. So the molecules or the atoms that make up these materials have rearranged themselves into new substances. To write a chemical equation, you, again, start with an arrow that separates the reactants from the products. Every chemical equation is essentially centered around this arrow, this transformation. And reactants are written on the left side of the arrow, and products are written on the right side of the arrow. If you have multiple reactants or products, which is often the case, you separate them with a positive sign. You're adding these things together, you're combining them together. Okay? We don't often use subtraction or a negative sign in a chemical equation, so always have a positive sign. Over the arrow, you'll often see a delta, which indicates that heat is used to start the reaction. There may also be other material formulas or substance formulas put over the arrow to indicate that they are catalysts, but that is a topic we'll get to much later. So for now, the thing over the arrow is just something that helps promote the reaction. That's the way you can think about it. So you would have one reactant plus another reactant transforms into one product and another product. Okay, and it does so, in this case, if you add a little bit of heat to it. That's what this delta sign, the triangle, is for. And often in most chemical reactions or most complete chemical equations, you should also indicate the physical states of the substances that are on both sides of the equation. So if your substances are in the solid state, you put a parentheses S after it. Liquid state is L, gaseous state is G, and then there's also the aqueous state, AQ, which means that the substance is dissolved in water. Okay, and we'll come to that a little bit later as well. Here's a table just reminding you of some of these features of a typical chemical equation. One of the most important things to understand about a chemical equation is that it should always be balanced. Just the way a mathematical equation should be equal on both sides in order for it to be true, a chemical equation also has to be equal on both sides in a sense. And well, how do we mean for it to be equal? Well, what we mean is that the atoms that go into the reaction are the same atoms that come out of the reaction, okay? No atoms are lost or gained during the course of the reaction, okay, of a typical chemical reaction. So the number of atoms on the reactant side equals the number of atoms on the product side. Not just the number of total atoms, but the number of each kind of atom. So in this case, imagine we had a reaction between hydrogen gas and oxygen gas. Okay? Hydrogen gas is diatomic, so each hydrogen gas molecule is really two hydrogens together, right? So here we have like two hydrogen molecules. And the same thing with oxygen. If we have an oxygen molecule, it's really two oxygen atoms together. So we can have two hydrogen molecules and one oxygen molecule, but really it represents four hydrogen atoms and two oxygen atoms. And so if they react together, they can rearrange themselves so that the oxygen, each oxygen atom, becomes connected to two hydrogen atoms. Okay? And so you end up with this. So you started with two hydrogen molecules and an oxygen molecule, and you ended up with two water molecules, because an oxygen atom with two hydrogens stuck to it is a water molecule. And so by doing it this way, by looking at it this way, you can see that this equation is balanced. You had four hydrogen atoms on the left, you still have four hydrogen atoms on the right. You had two oxygen atoms on the left, you still have two oxygen atoms on the right. They're just connected in a different pattern. There's just a different structure to them, to the molecules that they form. So let's start by doing an example. Moving on to the next example, we have aluminum reacting with iron 3 oxide to produce iron and aluminum oxide. So the aluminum and the iron sort of switch places in this reaction. That'll be a common theme we'll see later on. So let's just go through and count up all of each type of atom here. So in this case, we don't just have two elements, we actually have three elements. We have aluminum, we have iron, and we have oxygen. So if we write a table to keep track of all this, we're going to need an entry for each of these elements. Okay, so the first one is aluminum. We have this 2 here, which means 2 of whatever follows it, but whatever follows it is just, in this case, a single aluminum atom. So 2 times 1 gives you a total of 2 aluminum atoms. Okay. In this second reactant, iron oxide, there's no number in front, which again just means that that's just a 1. So that's where this is 1 and this 1 comes from. And this is 1 unit of this iron oxide, which is 2 iron atoms. That's where this 2 is. So 1 times 2 gives you 2 iron atoms. And then 3 oxygen atoms. So 1 times 3 gives you 3 oxygen atoms. Okay, so 2 aluminum, 2 iron, and 3 oxygen on the reactant side. On the product side, we have a 2 in front of the iron. Okay, so 2, let's look at, these are a little bit out of order on this side because things changed around. So now we're starting with iron, which is the second row. So the 2 in front of iron is this 2. But again, because there's no subscript, or you assume the subscript is 1, 2 times 1 is just 2 iron atoms. Okay? And then in the second product, you have aluminum oxide, so going back up to the aluminum row, again, this is just a 1 in front here, which is what this one is, and this one gets multiplied by this 2, right? Each unit has 2 aluminum atoms. So one of these has just 2 aluminum atoms in total. Okay? But this formula unit has 3 oxygens, so 1 times the 3 oxygens per unit gives you a total of 3 oxygens on the right-hand side. And so again, this is also balanced. You have 2 aluminums on both sides, 2 irons on both sides, and 3 oxygens on both sides. So this equation is balanced. This is a slightly more challenging problem that you might get. Instead of giving you the equation and just explicitly asking you to balance it, they're describing what happens in the chemical reaction, and then you are expected to do 2 things. The first is to actually generate the formulas in the chemical equation itself from this description, and then the second step would be to balance that once you have it. So to analyze the problem, again, remember, before we begin with the equation, we need to think about what's going into the reaction and what's coming out of the reaction, okay? And a word problem like this, it does give you that information, but it might not be obvious at first, right? It's giving you the reactants and the products, but it's really describing them or naming them, okay? And so we need to figure out how to translate those names into formulas, okay? And then ultimately we're going to need a balanced equation. So once we have the formulas in the equation, then we need to go through and count atoms on both sides, okay? So to begin with, what are the reactants? Well, the problem says that you have solid Fe3O4 reacting or reacts with hydrogen gas. So these are our reactants, and we can write them just like that. They tell us Fe3O4 plus, I'm just going to call it hydrogen gas for now, not worry about that too much. Okay? And these are producing, right? This word produce means they are creating or generating or transforming into solid iron, okay? That's one of our products, and water. Okay? So I can write it out just in words like this. I can take this paragraph, this word problem, and translate it into almost a chemical equation, where instead of giving specific formulas, I'm giving the names of the substances. And then I have to think about how to get the formulas. Okay? Fe3O4, they gave us the formula, so that was nice. We don't have to think about that. But the other thing about a chemical equation is we want to say what state these substances are in. So this one is telling us that it's solid, so we're going to put an S in parentheses after it. The next part is hydrogen gas. Hydrogen is obviously chemical symbol H, but hydrogen gas means hydrogen in its normal natural state, which again is always H2 molecules. So keep that in mind. When you're dealing with hydrogen gas, it's always H2. Same thing as with oxygen gas, it's always O2. And since we're dealing with a gas, right, the physical state of matter is gas. So you put G for gas after it. Okay? And so that's the reactant side. On the product side, the first product that we have is solid iron. Okay? Just iron by itself is Fe. We don't have to worry about a subscript or anything like that, but it's in the solid form, it tells us, so we're going to put the S after it. Okay? And then the last one is water, and you should know that the formula for water is H2O. If you don't know that yet, you should learn that now. And water is obviously in the liquid state. Okay, so the only time they don't give you something is when it's something like water, which should be pretty obvious. Everything else, they basically specify exactly what you need to know. And so this is the outline of the chemical equation. This is basically step one, right? So we have the formulas for each of the substances involved, and we've put them on the correct side, identifying them as reactants on the left versus products on the right, separated by a chemical equation arrow. Okay, so this is step one. Step two is to count up each type of atom. So in this case, we have iron, oxygen, and hydrogen. We have three different elements involved. So we need 3 rows in our table where we're counting atoms. Okay. When you get really good at this, you're not going to have to write down the table. But definitely at the very beginning, you should explicitly write out the table, because having in front of you is going to help you balance it much more easily than trying to just change the coefficients and look and see, keep straight in your head what's actually been changed. Okay, so at the beginning we have the reactants, which are Fe3O4. Okay, so 1 unit of Fe3O4 means 1 times 3 is 3 iron atoms, and 1 times 4 gives you 4 oxygen atoms. Okay, the coefficient in front times the subscripts, right? 3 and 4. For H2, we just have 1 molecule of H2 again, right? So we just have this one here, but it's an H2 molecule, meaning it's 2 atoms of hydrogen. So we actually have in total 2 atoms of hydrogen on the left-hand side. On the right-hand side, we start with just a single atom of iron. We haven't added anything to it. We haven't taken more than one of it yet. We just put it in there because we know we're going to get iron. So for now, we just have 1 of a single iron atom. So that's 1. For the molecule of water, we again have a 1 in front. Right, let me put that there. We again have 1 molecule of water. That 1 molecule of water involves 1 oxygen atom, right? So a total of 1 oxygens. And the 1 molecule has 2 hydrogen atoms. So that's a total of 2 hydrogen atoms on the right side. Okay. So we can see that the iron is not balanced, the oxygen is not balanced, the hydrogen does happen to be balanced, but that doesn't really matter, because once something else isn't balanced, we're going to have to go through the whole process, and it may turn out that the hydrogen changes as well as a result. So step 2 is just adding these up and seeing whether it's balanced or not. In this case, it is not balanced. That means that we need to go through and add coefficients. So again, we can start with the most complex formula. Now, this is a trick that you can use. Start with the most complex formula and put the coefficients in, like I said. If you can't tell which is the most complex, or there's some question, or you just don't want to do it that way, you can also always just start at the first element and work your way methodically through each row. Okay. For this case, we're going to start with the most complex formula, which is pretty clearly Fe3O4. Okay, so that means if we have Fe3O4 on the left side, then if we want 3 iron atoms, right, we have 3 iron atoms in the reactants. In order to get 3 iron atoms in the product side, we have to put this 3 in front. Okay, again, we can't change a 3 down here. We can't just arbitrarily put a 3 as a subscript after the Fe, because we have no reason to believe that iron is grouped into, groups of 3 atoms. There's nothing telling us that, and we don't know that. So that's not, in fact, how iron is. So you can't do that. But you can put the 3 in front as a coefficient. And so that gives you 3 iron atoms. And so now iron is balanced. Okay. And then we can do basically the same thing with oxygen. We know that we need 4 oxygen atoms. On the right-hand side, the only place that oxygen shows up is in a water molecule. If each water molecule has 1 oxygen atom, right, we can't just change this to H2O4. That could be an entirely different compound that doesn't come out of this reaction. It has totally different properties. So we can't just add the 4 there. We have to add the 4 in front as a coefficient again. Okay, so we add it here, and that gives us 4 oxygens. Now here's the tricky part, because we added this 4 here, and that gave us 4 oxygens, but it also changed the hydrogen, right? It's in front of the entire water molecule. So if we have 4 water molecules, this number now changes. Each water molecule has 2 hydrogens times 4 molecules gives us a total of 8 hydrogen atoms on the right-hand side. Okay? So that means that by balancing the iron and the oxygen, we've unbalanced the hydrogen for a moment. Okay? And so to fix that, we have to go back to the left-hand side and put this 4 in front. Okay? That's going to give us 8 on the left-hand side, because the hydrogens come in groups of 2, they come in pairs on the left-hand side. We need 4 pairs to get 8 atoms. So 4 times 2 gives us 8. So even though from the iron oxide we only needed to add this coefficient and this coefficient, that threw off the hydrogen, and so then we needed to go back and check the hydrogen coefficient and fix that. Okay? So again, the tip is to start with the most complex formula. The sort of other side of that is end with the simplest formula. So if you have a formula that's just one element by itself, it's often easiest to leave that until the end, because you can then add coefficients in front of that without throwing off anything else. Okay? And so then the final step is really just to check that we have actually balanced it, and to see if we have it reduced to the smallest whole number ratio. So in this case, we just double check our math, and we see that we have 3 iron atoms on both sides, 4 oxygen atoms on both sides, and 8 hydrogen atoms on both sides. And so it is balanced, and there's no common factor that we can pull out of these coefficients, so we can just leave it like this. And so what we end up with is 1 unit of iron oxide plus 4 hydrogen molecules gives you 3 iron atoms and 4 water molecules. Okay? And this is the balanced chemical reaction. As we saw in the previous examples, if you're creating a table to keep track of all of the atoms in your reaction, you need a separate row for each element. Some reactions, however, involve polyatomic ions, and polyatomic ions typically stay together during the course of a reaction. Okay? There are some cases where a polyatomic ion will be created or destroyed by separating the atoms in the middle, or sticking the atoms together in the first place. But usually, if you have equations or reactions involving polyatomic ions, the same polyatomic ion shows up on both sides of the equation. And so what that means is we can actually balance the polyatomic ion as its own separate entity without looking at the individual atoms that make it up. So this is an example of this type of chemical reaction where we would be able to do that. We have sodium phosphate plus magnesium chloride, and these react together in a precipitation reaction to give us magnesium phosphate and sodium chloride. Okay? But if you look at this, it's clearly not balanced. You can just look at the first atom, sodium. There's 3 on the left, and there's only 1 on the right. So it's clearly not balanced, right? So the first thing we have to do, in this case, is just given to us, right? They gave us the chemical equation, and we already looked at it and saw that it's not balanced. And so now we need to create our table. So step 2 is to create the table, but in this case, instead of having a separate line for each type of element, we're going to have a separate line for each type of ion. Okay? So on the left-hand side, you have sodium phosphate, which is sodium ions and phosphate ions, right here and here. And on the right-hand side, you also have phosphate ions in the magnesium phosphate, and you have sodium ions in the sodium chloride. Okay? So you can see that the ions are there on both sides. Same thing with magnesium chloride. You have the magnesium ion here and the magnesium ion here. Okay? It's the same on both sides. The chloride ion is here, the chloride ion is here. It's the same on both sides. Okay? So because of this, because the phosphate in particular doesn't break apart into individual or separate phosphorus and oxygen atoms, then we don't need to consider the phosphorus and the oxygen separately. All of the phosphorus is in the ions here, and it's all in ions on this side. All of the oxygen is there, and all the oxygen is here. Okay? Sometimes you may have oxygen on the outside, which complicates it. You need to balance it separately. But for this case, that's not going to be an issue. Okay? So we just see that we can consider phosphate as its own entry in the table without having separate lines for phosphorus and oxygen. So let's start the count. Okay, on the left-hand side, we have, again, a 1 in front, and then sodium phosphate has 3 sodium ions. So 1 times 3 gives you a total of 3 sodium ions on the left. Okay. On the right-hand side, I'll go element or ion by ion. So on the right-hand side, we have just this single sodium ion, right? There's a 1 in front here, and you also can assume this is a 1 subscript, so 1 times 1 gives you 1 sodium ion. So again, not balanced. We already saw that. Going to the next row, we're dealing with a phosphate ion. So on the left-hand side, we have 1 phosphate ion. Okay? Don't get confused by this 4 here. That 4 just means that in that phosphate ion, there are 4 oxygen atoms. Okay? But it's just 1 phosphate ion attached to the 3 sodium ions. Okay? So it's just 1 phosphate on the left-hand side. On the right-hand side, we have the phosphate here, and it's in parentheses. And so the number outside the parentheses indicates how many of those we have. So we actually have 2 phosphates in each unit of magnesium phosphate. Okay? We only have 1 unit of magnesium phosphate, that's this one, but this 2 subscript is here. So 1 times 2 tells us that we have 2 phosphate ions. Okay? Again, not balanced. The next ion is magnesium. We have 1 on this side, and we have 3 over here, right? The 3 subscript means this formula unit has 3 magnesium ions, right? One of those units, 3 magnesiums each, gives us 3 magnesiums. And then the last ion is chloride. On the left-hand side, we have 1 magnesium chloride, but it has 2 chloride ions in it, so that's a total of 2 chloride ions. And on the right-hand side, we have 1 sodium chloride. Each sodium chloride only has 1 chloride. So if we only have 1 of those, that's 1 chloride ion. Okay? And so again, none of these ions are balanced here. So we're going to have to do some balancing in order to make this work. That brings us to step 3, which is to use coefficients to balance the equation. And again, we can't change the formulas because the formulas are set by the type of substances that are involved in the reaction. So we can't go around changing subscripts in the individual formulas for these substances. The only thing that we can do is put a number in front, which indicates that we're taking a certain number of each of those units or molecules. And so mathematically, that means we're multiplying by that number. So the tip is, again, to start with the most complicated or complex formula, which in this case would be magnesium phosphate, the product, okay, which is 3 magnesium ions and 2 phosphate ions. So if we need 3 magnesium ions, right, we have 3 magnesium on the right-hand side. So if we need 3 on the left-hand side, we have to put a 3 in front of the formula that includes magnesium. Okay, that changes this to a 3 and gives us 3 magnesium ions. And so we're good. And then if we want 2 phosphates, right, we have 2 phosphates on the right-hand side, then we need to put this 2 here in front of the formula with phosphate in it. That changes this to a 2, and so we end up with, again, 2 phosphates. So this has allowed us to balance the phosphate and magnesium ions. So those are done, at least for now. But those 2 numbers that we added, this coefficient and this coefficient, had other effects, right? Putting this 3 here changed this to a 3 as well. And so since 3 magnesium chlorides, each magnesium chloride has 2 chloride ions, taking 3 of them actually gives us 6 chloride ions on the left-hand side. And this 2 here in front of sodium phosphate means that we take 2 sodium phosphate units, and each sodium phosphate unit, right, this is 2, and each sodium phosphate unit contains 3 sodium ions, and so that gives us 6 sodium ions. Lucky for us, on the right-hand side, sodium and chloride are together as NaCl, just one of each stuck together. So if we need 6 sodium and 6 chlorine, we can just put this 6 here, and it will balance that out. So we end up with the correct number of sodiums and the correct number of chlorides. Again, step 4 is just double checking that count and then seeing if we can factor out any common multiples or common factors from the coefficients. In this case, we definitely can't factor anything out. We have even and odd numbers, nothing has a common factor, so we're okay there. And we can just double check. We have 6 sodiums on both sides, we have 2 phosphates on both sides, we have 3 magnesiums on both sides, and we have 6 chlorides on both sides. Okay, and so we're done. It's perfectly balanced. And we didn't need to balance the phosphorus separately or the oxygen separately. We were able to just balance phosphate as its own entity. So let's balance a few more as an example. I'm just going to go through these quickly. You can try and do them a little more methodically on your own if you need help. But again, we'll start with the most complex formula. We have 2 irons in that, which means I'm going to try and put a 2 here. And we have 3 oxygens, which means, well, it means I come with a problem. Okay, the oxygen on the right-hand side is only in CO2. And that means that it comes 2 at a time. Okay, so I can't get 3 oxygens from a molecule of CO2 or 2 molecules of CO2. I can only get pairs of oxygens or even numbers of oxygens. So when I encounter something like that, I need to go back and then put a 2 here. Okay? That's going to give me an even number of oxygens. If I take 2 iron oxides, each one has 3 oxygens, now I have 6 oxygens. Okay? And to get 6 oxygens on the right, I can just put a 3 in front here. The problem with that is it throws off my iron coefficient here because I don't have just 2 iron atoms on the left. Now I have 4 iron on the left. So I can add that 4 here to make that balanced. And then the last thing that I need to balance is carbon. On the right-hand side, I have 3 carbon dioxide molecules. Each has a single carbon, so that's 3 carbons. On the left-hand side, I just have carbon atoms by themselves, so I'll take 3 of those to balance this out. Okay. So that means the coefficients in the order they're given here are 2, 3, 4, 3. 2, 3, 4, 3. That means our answer is B. Okay. For number 2, we have aluminum plus iron oxide gives you iron plus aluminum oxide. Again, this is the most complex formula, aluminum oxide. So I'll take the 2 aluminum atoms and put a 2 in front here. And I'll take the 3 oxygen atoms, and this time oxygen, it's with iron, but it's just single oxygen atoms. And iron oxide in this formula, this is iron 2 oxide, it doesn't have more than 1 oxygen, so I can just put the 3 in front here. Okay, and that'll give me 3 oxygens on the left-hand side. That also gives me 3 irons, which means I then need to change this to 3 to get 3 irons. Okay. Then I can also remember that if I left the coefficient blank, like I did here, that really means 1. Okay? If you don't put a coefficient in, don't think that it means 0 or something like that. It means 1. So in this case, the answer is 2, 3, 3, 1, A. In the last one, again, we can go to the most complicated formula, which is aluminum sulfate. Okay? Aluminum, there's 2 of those, so I'll put a 2 here. And there are 3 sulfates, right? The sulfate is a thing in the parentheses, SO4. This outside the parentheses means we have 3 of them. Okay? Sulfate on the left-hand side is in sulfuric acid, H2SO4. There's just 1 sulfate in that formula. So I'll need to put the 3 here to get 3 sulfates on the left-hand side. That's going to leave me with 3 times 2 hydrogens, which is 6 hydrogens. On the right-hand side, I have pairs of hydrogens, right? Hydrogen gas molecules are pairs of hydrogen. So if I need 6, well, I'll need 3 of those. Okay? Then I can put my 1 in here since it's blank, and I get 2, 3, 1, 3, B. So go through these on your own. Make sure that you get the sense of it, how to balance these, that you make sure that when you change the coefficient in front of a compound, that you distribute that change to both of the elements or all of the elements, if there are more than 2, in that compound. Okay? And make sure that you follow through the logic to balance these equations.